Welcome to the stoichiometry video. This will be at least the first one of the videos for stoichiometry, and there will be at least one more video that goes into some more difficult problems. And I say this is at least the first one because stoichiometry really does branch into other areas of higher level chemistry. And so there could someday be some videos on those things as well. So whether you're in a high school class or a college course or even AP, which is also high school, right, but higher level, this could help you out with the basics of stoichiometry to help you with more difficult problems in the future. So don't let that scare you off. A lot of these videos say that they start out with the basics and then we're going to build into the higher level, more difficult problems. But stoichiometry is one of the reasons why I really do love chemistry. I love all the color changes and stuff like that, but I really drive myself with some of the math problems that chemistry throws at you. And stoichiometry tends to be one of the first things that you start doing all the math problems with. So what is stoichiometry? It's just going to be unit conversions, and you probably have done them before, but it's going to be more of a chemistry termed unit conversions. So when I say that, we're going to figure out what a mole is in this video and how to convert moles to different things. So that's as basic as I can break it down, and we'll get into those into more detail. During this video, the first thing I'm going to show you is a really simplistic diagram that you'll want to take a screenshot of. And then from that diagram, I'm going to show some notes that go into each of the branches. And afterwards, we'll start out with some one-step, simple, straightforward stoichiometry problems. And then in the next couple of videos, or at least the next one, we'll go into some of the more difficult multi-step problems. So stay with me. By the end of the videos, you should be ready to go with any problem that's thrown your way. Pay attention to some of the directions. Sometimes we can switch up how we ask to calculate something. And so that can be very important in you even starting your approach to your problems. So let's go ahead and get started before I make this any longer. All right. This is a diagram that I would like you at some point to go ahead and pause the video and take a screenshot of it or write it down in some fashion, because this is really just a snapshot of what stoichiometry is. Of course, we'll go into what moles are. I mean, that's the biggest part of this whole entire diagram is that big circle kind of hitting you square in the nose. That everything's going to be around moles. Okay, so we want to convert between moles to something else, and that something else is the three different branches that are on the outside. We're going to use this stoichiometry for like these one-step problems. We're going to have two-step problems, and we're going to get into, like a balanced chemical reaction and be able to do a bunch of stuff because of this diagram. Okay, so starting out at the very top, we can go from atoms, molecules, or particles back and forth between those to moles. And you can see that's by Avogadro's number. And so whether your teacher makes you memorize that or gives you that, everything that's in that part of the diagram revolves around the 6.022 times 10 to the 23rd power. And we'll talk about that more in detail a little bit later. The next part of the branches that we'll be talking about is down to your bottom left, which is moles to grams or grams back to moles. And we need to know what molar mass is to be able to do those calculations. Over to the bottom right-hand side, we can also do some calculations between moles and volume. And you see liters are written down there, And the way that we're going to go ahead and go and convert between those two is by 22.4. At STP, and I'll elaborate with what STP means when we talk about that branch. The big thing I really want to point out here, to really simplify this as much as possible, is whenever you're going from moles, so the center part of this diagram, out to any of these three branches, you're going to have to multiply. Okay, so every single time you're going from moles to something else, you multiply. If we're going from one of the outside branches back to moles, okay, so the big thing is if you want to go back to moles, you have a division problem. And so every single step that you're going to be looking at is either going to be multiplication or division. So don't let this stuff scare you. at this point, we're going to break down each one of the branches from a couple of notes. And again, we're going to start with the very top, which is the green, and then we'll go down to grams, which is the bottom left, and then we'll go over to the bottom right for liters. So let's go ahead and get that part started. So the first branch that we're going to talk about, I kept it in green so that you can kind of visualize okay, start over. So the first branch that we're going to talk about is the moles, atoms, molecules, or particles, which was green on the last diagram page that you can look back to. And so visually, hopefully you can connect those two. You can also see over to the top right here, in parentheses, I put representative particles or formula units, because I've seen some problems where they also use that kind of vocabulary to ask these questions. The big thing here is whether you have an atom or a molecule or any one of these 5 things that are written down, the same math applies to go from moles to one of them or back, okay? And again, just like our first page said, everything's going to revolve around Avogadro's number, which I have listed here. But also note I have some units at the end of this. And this is going to help us set up our problems when we get into doing some examples. So if we break down this number right here, the 6.022 times 10 to the 23rd, we have atoms over moles. And so some students have a hard time wrapping their heads around what this actually means, or better yet, even just how to plug it into a problem. And so we'll see that in a little bit and how to apply that. But a really simple way to convert this to kind of plug it into things is right here. So this means the same exact thing as the number that's right above it. What it says is 6.022 times 10 to the 23rd atoms equals 1 mole. And so we care about this a lot in chemistry because if we were looking at the weight or the mass of one atom, first of all, we can't visualize one atom very well. We would need a model for that. And the weight of an atom is very, very small. And so this amount of atoms, we actually could weigh them out. We could go ahead and actually visualize how many grams that's going to be. And so we can also compare molecular weights, which we'll get to in a little bit. So looking at any periodic table, every single, square or rectangle, whatever shape you might have for your periodic table, that is, each element has a mass underneath of the symbol for that element. And that mass is going to be the mass for 1 mole of that element. So for instance, on my periodic table, hydrogen's mass is 1.01. So for 1 mole of hydrogen, 1 mole of hydrogen weighs 1.01 grams. Another way we can look at it is for 6.022 times 10 to the 23rd atoms of hydrogen, the mass of it would be 1.01. Another way some teachers will teach, how to compare this number equals 1 mole is that we grow up knowing that 12 eggs equal 1 dozen eggs. So really 12 of anything equals 1 dozen. So if you compare the left to the right, you can see that replace dozen with mole and replace this part, the number and the eggs, with Avogadro's number. It's just a ratio between 2 things. And so sometimes it helps people kind of break it down that way. We'll be looking at the conversion between moles to grams and vice versa. One thing I want to point out is molar mass is on your diagram, but that is also known as molecular weight. And so some textbooks might call it one or the other, or teachers might interchangeably say these 2 different terms, molar mass versus molecular weight. You just need to be aware that they mean the same exact thing. So you could Google both of them and they're going to pop up with the same type of work. Molar mass is something that we're going to have to calculate before you do any of the work between moles to grams or grams back to moles. And so unlike the last branch, using Avogadro's number, we don't have one number that's going to work for all these problems. We actually need to calculate it. So a lot of students start out thinking it's 2 problems when they start doing this branch of stoichiometry, but you get quick at it, okay? So practice it, you'll get better at it, it'll get quicker. So let's go ahead and look at it. So let's go ahead and look at a really simple example. I went ahead and did CH4, and I kept with CH4 because the math is really similar to how to calculate total valence electrons. And CH4 is what I did for that example in another video. So you could be watching through a lot of these videos and you'll see that similarity here. So let me go ahead and uncover that so you guys can see what this will look like, and we'll walk through it. So here's all the work for how to calculate molar mass for any compound for that matter, but we're going to break down CH4. It's simpler than some of the other ones you'll have, but really what you want to do is take CH4, break apart all the different elements that you have. And so in this CH4 we have carbon over here and hydrogen over to the left. And then you want to figure out how much of each of those elements you have. As you can see from the amount of each from the formula, we have 1 carbon and 4 hydrogens from this. And if this part is not making sense, please go back to the breaking down compounds, which is kind of with the balancing chemical reactions video. All right, so moving on from there, we want the amount of each, and then instead now we want to go ahead and multiply by the mass from the periodic table. So this might be a little bit different depending on what your periodic table is, but for my class we have 2 numbers past the decimal place for almost every single element except for the newer ones. So carbon on ours is 12.01 grams. And 1.01 grams for hydrogen. And remember, those weights are per 1 mole. So we'll just go ahead and multiply across and write down this number. Multiply across again and get this number. And how many numbers, it doesn't matter how many numbers you have listed here for your compound, you want to add them all together. And in this case we have 16.05 and our units will be grams over moles, which is the same thing as what I have written here. 16.05 grams of CH4, or methane, equals 1 mole of CH4, or methane. And so you can apply this work to any formula that you're given so that you can go ahead and calculate moles to grams or the vice versa of that. For this branch of the diagram, the moles to liters and vice versa, it's key to know the STP part, which I went ahead and underlined a few times right here to draw your eye to it. In order to do this branch of the diagram, you have to be at STP. And so we'll talk about what that is in just a second. It's also written on this piece of paper. The big thing to note is that this branch has everything to do with volume. If for some reason a question asks you, go from moles to volume, or what is the volume of this amount of moles or grams, it can be asked a lot of different ways, but you can convert from moles to liters. So what is STP? The second line says STP stands for standard temperature and pressure. And so this is going to be applied to not just chemistry, but other science courses as well. So you might be thinking about what is the standard temperature and what is the standard pressure, and that is highlighted and starred right here. You have to be at 0 degrees Celsius and 1 atm, which is also short for 1 atmosphere. Both of these conditions need to be met to be considered at STP. So if for some reason one of those 2 conditions is not met, you are not at STP and cannot do your problem. If you are at standard temperature and pressure, which means you're at 0 degrees C and 1 atm, you will need to use 22.4 liters over moles to go ahead and do your problem. And just like I promised, and throughout this video, I will try to show that as 22.4 liters is equivalent to 1 mole of anything at STP. So now that we've gone over every single branch in our diagram with additional notes as well, it's time to dive into the different examples that we can go over. And at first we're going to go ahead and try, from moles out to one of the branches and the vice versa. And then on the very last branch, we won't do both of them, but I will show you how density problems can be worked in with the volume part of our diagram. So we're going to start again with the moles to atoms, molecules, or particles, which is the branch that has everything to do with Avogadro's number, and keeping it in the same color as the diagram, which is green, so you can visually compare the two. The first example problem is calculate the number of molecules in 7.50 moles of SO2. And so the way we want to go ahead and set this up will be shown in just a moment. So here we have our dimensional analysis set up. Some teachers call it the factor label method, but really we just need to break down how to go about doing this problem. And there's different ways that you can diagram a T-diagram or the work that you're trying to show. And you want to try to show your work because when you get to higher up or harder problems, showing the easy problems this way will help you realize how to set up your harder problems. So please try to set them up in this fashion. Whatever is given to you in the problem. So a lot of students forget to come back to the very beginning. So the 7.50 moles of SO2, and that will always go in your first box here. Because we have solid units where we're not having moles over something else, this box is going to be left blank, and you should have a value of 1 in there. Some teachers will tell people to put like smiley faces in there or X it out, but I feel like the best practice is to really think that it's over 1. In the next box here, there's 2 ways to think about how to set this up. We need Avogadro's number, and remember 6.022 times 10 to the 23rd is equivalent to 1 mole of whatever molecule you're looking at in this case, or atoms or particles. And so because moles are on top here, you want moles on the bottom. Another way to look at this problem and how to get it set up would be when you're going moles to molecules, you would want to multiply, and anything that's on the top would be multiplication. Anything on the bottom that you place on the bottom would be like a division problem. And so because of the work that we do here, we can go ahead and do 7.50 times Avogadro's number. And if you have a number other than 1 on the bottom, you would divide by that. When we input our numbers on the calculator, this should be the answer that you receive, the 4.52 times 10 to the 24th, molecules of SO2. And you do want to get into the practice of when you do scientific notation to put parentheses around your entire number. So I'm going to write a little note in here showing you how it would look on a calculator. So on your screen now in red, you can see how you would want to enter scientific notation on a calculator. And you want to pay attention to this because if you don't do it this way, you'll end up with answers that are not correct. So please put your scientific notation inside parentheses just to make sure there's no issues in the future. So again, just to summarize this, when you go to moles to any of the 3 that are at the top, atoms, molecules, particles, remember you can do representative particles or formula units as well. You want to multiply, and this would be how you set up your problem. For the opposite problem, going from the outer branch back to moles, we are going to want to divide. And so here is an example problem of that. It says find the number of moles in 9.03 times 10 to the 24th atoms of mercury or Hg, as it's written here. So we want to take what's given to us, set it up in the very first box, but in this case atoms will be at the top, so you'll want atoms to be on the bottom. The number that goes with atoms will be Avogadro's number. So let's see how that's set up. So here on the screen you can see all of the work, including the answer. Just like I was stating before, you want to put what's given to you from the problem in the first part. But in this case, we want to divide by Avogadro's number. And the Avogadro's number goes with our term atoms. And since we're talking about an element or an atom of mercury, that is why we're in atoms. The problem before was in molecules because we're talking about a compound of SO2. And so in this problem, the easiest way to describe this to a whole bunch of people would be you want to multiply across, so you take the 9.03 times 10 to the 24th times 1, and then you would divide by the number that's on the bottom. And so your resulting number would be 14.99 with some more decimals behind that. But we want 3 sig figs, so we would need to round that to 15.0 moles of Hg. At this point, it's time to go into another branch. Again, we'll show a forward way and a backwards way, basically going from moles to grams and grams back to moles. And so let's go ahead and get into this part of the diagram. Our first example problem is calculate the mass in grams of 0.25 moles of SO2. And so I'll go ahead and show the molar mass. You can always pause the video and go back to your notes or re-watch how to do molar mass, but we'll quickly go over how to do this for SO2. So here on the screen you have the work for the molar mass of SO2. Break down your compounds, so S and O, and you have 1 of sulfur and 2 of oxygens. You want to multiply it by the weight off the periodic table, and then once you multiply both of those, you want to add them together. And so we have a molar mass of 64.06 grams per mole. Our molar mass, in my classes at least, will always have 2 past the decimal place because of how the periodic table is set up in my classroom. And we always need to remember that our units for molar mass are grams over moles. You can see a little note underneath that saying that you should remember that grams over moles can really be broken down into this simple conversion factor here. You can think of it as 64.06 grams of SO2 equals 1 mole of SO2. And sometimes students can see what plugs into their problem when they set up their dimensional analysis better by seeing it written out this way. So let's go ahead and get this set up. Whatever is given to us, which I want to note that now because it's going to come off of the screen once I show it, but we start with 0.250 moles of SO2. So I kept the remember note at the top so you can see how that will plug into our setup here. Again, you have the 0.250 moles of SO2 in the starting box. Remember that's over nothing here, but it's over 1 is what we really should be visualizing it as. If we go from moles to anything out to one of the branches, such as grams in this point, we want to multiply. So that's why we have 64.06 grams of SO2 on top and moles on the bottom. Another way of looking at this is if we have moles on top, we want moles on bottom, so those will cross out units, and we'll be left with grams of SO2 at the end. Go ahead and multiply these numbers across, and you would divide by 1, giving us 16.0 grams that you see on your screen. Alright, so let's go over an example problem where we're doing the opposite of what we just saw. This is going to be example 4, or the second example of moles to grams and the vice versa for the blue part of our diagram. This says calculate the number of moles in 1.00 times 10 to the second grams of SO2. And so that number is what we want to start with. We want to also realize that we have SO2 still, and so we can use the same molecular weight that we were using before. So let's go ahead and show the setup of this, and I'll actually show how you can cross out your units since I've been mentioning that in the other examples and haven't shown that yet. So here in this example you have what's given to you right here, and this time we want to divide by the molecular weight. This will also allow us for the grams to be crossed out, and you'll be left with moles. The moles of SO2 will be the only unit that's not crossed out once we go ahead and get that done. And you can see that our answers need to be 3 sig figs in this case too. So 1.56 moles of SO2 will be your answer. And let's see how we would go about crossing out our units. When you cross out, one of the big mistakes is only units get crossed out, not the numbers. So the grams of SO2 on top and bottom would be crossed out. So that's what I was meaning by crossing out in some of the earlier examples. Just a reminder, the zeros here do count for significant figures, and that's where I got the 3 sig figs from. We are now on the last branch of the diagram, which is moles to liters. We have to remember that we have to be at standard temperature and pressure, which is abbreviated STP. And we also should kind of relate this branch of the diagram to volume. So we can convert moles to volume, and obviously you can always do a dimensional analysis between liters to some other unit or quantity of volume. For our first example, we're going to go ahead and do the following. Calculate the volume in liters of 1.34 moles of SO2 at STP. We're only going to do moles to liters for this one and not the vice versa, because we've gone through every single type of forwards and backwards to each part of the diagram, and I don't think that needs to be shown again. So let's go ahead and get our setup started with the 1.34 moles of SO2 in the beginning part. And remember, this part of our diagram is going to use the magic number of 22.4. That's going to be liters per mole for the units on that. So here you can see 1.34 moles of SO2 starts our diagram, and we have 22.4 liters on top because we want the moles to cross out. So let's go ahead and get those moles crossed out. And I'm also going to rewrite that the 22.4 liters of SO2 should equal 1 mole of SO2 so that you can kind of see how things plug in. So let's give that a try. So here you can now see how the moles cross out, and I actually went ahead and kind of did a separate SO2 cross out. So all the units cross out on the top and the bottom here and here. The other thing I wanted to show you, just in case you're wondering where this was coming from, and my explanation didn't help too much, the 22.4 liters per mole is the magic number that I mentioned before I showed the setup. This is the same as saying that 22.4 liters equals 1 mole. Before we go on to another example, I do need to point out here again that you cannot do these problems unless you have something that says it's at STP, or it actually lists out what the standard temperature and the standard pressure are, which would be 0 degrees Celsius and 1 atm. So be careful here, because if you have anything other than STP, you cannot do this type of problem. Our next and last example problem is what is the density of SO2 gas at STP? And so we can use this branch to figure out the volume, and we can also figure out molar mass at this point in time. So there's a few things we need to remember. We need to first remember that density equals mass divided by volume. Keep in mind, for a lot of these, you're going to want the mass in grams and the volume in liters. However, a teacher could go ahead and change the final units that they want to something other than this, but these grams and liters are really the units you're going to want to be able to solve the problem from the get-go. We need to also assume we have 1 mole of SO2. In the problem itself, it doesn't give you any quantity of how much SO2 you have. So assuming that we have 1 mole will make this problem quite straightforward. So the next 2 things that you need to think about, since we now established we need to assume 1 mole of SO2, is that 1 mole of SO2 is the same thing as having the molar mass of SO2. And so 1 mole of SO2 would then therefore mean that we have 64.06 grams of SO2. If you didn't have SO2 in this problem, since we've been consistent with SO2 throughout our example problems for the most part, you would have to calculate the molar mass, which you should know how to do at this point in time in the video. The next thing, and this is part of the branch that we're working on, is we also need to know that 1 mole of SO2 is equivalent to 22.4 liters of SO2. And once you get the molar mass and realize that you have 22.4 liters of SO2, or whatever compound or atom you're doing in that case, you're just going to go ahead and plug that into the density formula. So I'm going to move this up and show you how the setup would work, and then hopefully it will become pretty straightforward from there on out with these different example problems. So moving this up a little bit, you can still see the notes that you need to take into account. You still want to figure out the density. I went ahead and plugged in your molar mass of 64.06 grams of SO2. Again, you have to calculate this if you don't know it already. 22.4 liters of SO2 should be pretty consistent as long as you're assuming 1 mole of whatever compound you're using or amount of atoms you're using, etc. And here I just want to point out that I had a little whoops. This should be grams over liters, since you have grams over liters when you plug in over here. So you have 2.86. The 6 comes from a rounding, so make sure you're rounding correctly. Grams per liter of SO2. So now that we're at the end of our example problems, I wanted to show you the diagram one more time, just to kind of conclude and bring this all to a circle. Every single one of these branches has a little bit more information that you should already have written down. But now that you look at each one of them, this diagram should make a little bit more sense. You're either going to multiply or divide for every single one of the branches. For every time you go from a mole to any of the outside branches, you are going to be multiplying. And if you want to go from a branch back to moles, we need to go ahead and divide. Moles is a smaller quantity and should be smaller when you go ahead and do your calculations. On here, it also tells you what you need to multiply and divide by. Maybe this will be a little bit more apparent now that you've gone over everything. For grams, you want the molar mass. For atoms, molecules, and particles, you want Avogadro's number, and you want to do 22.4 for liters.